All right, everyone. Our homework last night was two sets of them. Page 52, a couple practice problems, and then page 53, our check and reflect questions, of which we had 14 questions, I think. Any issues, first of all, with the practice problems on page 52? Practice problems on page 52. They're both good? All right. Any issues with the check and reflect questions on page 53, 1 to 14? All right. 7 and 8. Any others? 7, 8? 10, 12, and 13? Okay, what we'll do here probably is take a look at them and okay. So, yeah, what I was going to say is we'll take a look at them and see if we can find some similarities. And, you know, if there's a couple that are kind of real similar to each other, we'll do one of those questions. So the issue you're having is the ones that don't have time in it. Okay. And that's, yeah, I guess that's all those questions, isn't it? Yeah. Okay. So it's probably going to be the same equation for each of them once we figure out exactly what that is. All right. Well, let's take a look at number 7 first. It says approaching a flashing pedestrian activated traffic light. The driver must slow down to a speed of 30 kilometers per hour. The crosswalk is 150 meters away. And the vehicle's initial speed is 50. What must be the magnitude of the car's acceleration to reach this speed limit? So this is a good question to go over first, actually, because it doesn't have the time. That was what you were having the issue with. But it also requires unit conversions. What is it that we have to convert here? Kilometers per hour to meters per second. If we're using vehicles delta D over delta T, our group A equation, then we could leave it in kilometers per hour if we want, because that equation can use kilometers per hour. Having said that, it's still not normal, but it's relatively common. When we're dealing with acceleration, okay, whether we use the term acceleration or the variable acceleration or not, doesn't matter. We've got to use meters per second. So let's circle that just to remind us when we go to write down our givens that we do have to convert that to meters per second. What I'm going to do actually is take a quick shot of that. All right, now we got a little bit more space there to work with. Let's write down some givens here. Something's 30 kilometers per hour. Doesn't give us a direction, north, south, east, west, so we just have to assume that it's moving in a positive direction, whatever direction that is, right? Something is also 150 meters. Something is 50 kilometers per hour. And obviously, we're looking for the acceleration here. What's the magnitude of the car's acceleration? All right, tell me what the 30 kilometers per hour is. VI, VF, V, delta V, what is it, Caden? Final velocity, so it has to slow down to a velocity of 30 kilometers per hour. Good. What's the 150 meters? It's the displacement. Good. Now somebody might say, well, isn't that distance? Yeah, it could be distance or displacement, right? It's in the same direction as the velocity, so we know that it's in the positive direction, whatever direction that is. We can say it's displacement, but it is also distance. Since it hasn't changed direction, distance and displacement have the same value. Tell me what the 50 kilometers per hour is. It's the what? It's the initial velocity, right. All right, now before we do any more, let's do the conversion here. 30 kilometers per hour, meters per second. We've got to multiply by 1,000, divide by 3,600. 30,000 meters divided by 3,600 seconds gives me what? 8.3 repeating, so we'll say 8.3333 meters per second. Now 50 kilometers per hour is 50,000 meters over 3,600 seconds, which is 13.8 repeating. Unless we have a final answer, we want to go to 4 or 5 decimal places. So don't round that to 13.9 or 13.8 or even 13.89. Go to at least 4 decimal places like I have. Even more is better. All right, it's Group B. We already established that. Which equation of Group B do you want to try first? Again, the issue was, when Maureen asked this, the time. We don't have the time. that doesn't mean we can't use an equation with time in it. Okay, we can use an equation with time in it and solve for time. Maybe that'll help us with something else. But there might be an equation that we can do without time. Caden? Okay, let's take a look at that. Vf squared is equal to Vi squared plus 2a times delta d. We're solving for a. Okay, so let's rearrange the solve for a. Let's get rid of what's not attached first. What's not attached? Vi squared. So let's take the Vi squared over by subtracting. And now let's get rid of the 2 and the d. Can we get rid of those at the same time? Yeah, do we have to get rid of them at the same time? No, we don't have to, but we might as well. Vf squared minus Vi squared over 2 times delta d. So we've got now 8.333, 8.3 repeating, squared minus 13.8889 squared over 2 times the displacement was 150 meters. All right, take a look at how I do this on the calculator, okay? Let's say 8.3333 squared. Don't need to use a bracket there because we have this square button. That's good enough. Subtract 13.88889 squared. Let's press enter now. Okay, so we want the number on the top. Let's not try to get everything together. Okay, let's get the number on the top. And then let's divide that by, let's use some brackets here, 2 times 150. Notice where I used the brackets? Everything on the bottom was inside the brackets. The reason I did that is because if I do this, then my calculator will interpret that as whatever was on the top divided by 2. Then everything multiplied by 150. So we don't want to do that. We don't want to divide the top by 2 and then multiply everything by 150. We want to multiply the bottom by 150. In order to do that, I've got to get brackets. I've got to get brackets right here. Okay, brackets around everything. Does that make sense? Okay, what do we get when we do that? Negative 0.4115. We're going to round that to negative 0.41 meters per second squared. We're not overly concerned with significant figures yet, but in the end, this would be 2 digits. We'd round it to 2 digits because we look back to our original data. This is 3, this is 2, this is 2. We round to our least precise piece of data, so it would be 2 digits. Okay, I wouldn't take marks off on a quiz, though, if you get the sig figs wrong. Not yet, anyways. Maureen, is that okay? All right, let's take a look at another one here. As I said, we're probably going to find that a lot of these questions are similar to each other, but we'll take a look at least 2 of them here. Sorry? Yep. Number 8 says a train's stopping distance, even when full emergency brakes are engaged, is 1.3 kilometers. If the train was traveling at an initial velocity of 90, what's the acceleration under full emergency braking? So let's write down some givens here. It's accelerating or decelerating, right? So it's group B. What do we have given to us in this question? What's the 1.3? Distance or displacement, somebody said. We got to convert that to meters, right? But we'll worry about that after we have all our givens written down. What else do we have given to us in question number 8 here? 90 kilometers per hour, what's that? VI. We're also going to convert that to meters per second, but we'll worry about that again as well once we have all of our givens written down. We want to find the acceleration, that's what it says. Is there anything else we have if we read between the lines? Connor? Good. How do you know that VF is 0? Good. If we want this thing to stop, then obviously VF is going to be 0. So let's write that down. Let's do our conversions here now. First one's easy. 1.3 kilometers in meters is what? 1,300. 1.3 times 1,000 gives us 1,300 meters. Second one's not quite as easy, but you guys are getting really good at this now. 90 kilometers per hour is the same as 90,000 meters divided by 3,600 seconds. And that's going to give me 25 meters per second. All right, which equation do you want to use? Go ahead, Tanner. Yeah, we're going to use the same one as last time. Generally, if you're looking for a group B equation, but you don't have time given to you, generally you're going to use that equation. Okay, it's not the only way, but generally you're going to go with that. The f squared is equal to vi squared plus 2ad. We want to rearrange that this time and solve for a. I think that was the same as last time, actually. So we're going to take the, we can just cross that out if we want, 0. Take the vi squared over by subtracting. And now let's take the 2 delta d over by dividing. So it's going to be, just get rid of that 0, negative vi squared over 2 times delta d. So let's plug our numbers in here. We got negative 25 squared over 2 times 1.3 kilometers or 1,300 meters. Watch this one on the calculator, okay? Because this one, although it has one less variable, actually is probably harder to do on the calculator. We're not squaring everything here. Okay, what are we squaring? 25. Squaring negative 25 or 25? 25. Okay, so it's going to be negative 25 squared. Do not put brackets in there. Don't do this. If you squared negative 25, you're going to get positive 625. If you square 25 and then put a negative in front of it, you're going to get negative 625. What should we get? We should get the negative. Right? We should get the negative. So it's negative 25 squared, not negative inside brackets 25 squared. We're not squaring the negative there. Let's press equals. Let's divide that by, let's use some brackets outside of everything. 2 times 1,300. We end up getting negative 0.24. Should it be a negative value? Why? Yeah, it's slowing down. Why does this train decelerate so slowly, negative 0.24 meters per second squared? Why can't it slow down quicker? Sorry? Yeah, it's got a ton of kinetic energy, right? Because it's so massive. In Unit 2, we're going to talk about a concept called inertia as well. You may have heard that term before. If you ever watched Bill Nye, inertia is a property of matter in the opening song. Kinetic energy is kind of related to inertia in that sense, partially related to inertia in that, the more kinetic energy, the more inertia something has, the harder it is to stop. Is that okay, Wayne? 12? Now let's take a look at 12 now, and we'll see if that covers it for us.
Great.
Number 12, determine the magnitude of a car's acceleration if its stopping distance is 39 meters for an initial speed of 97 kilometers per hour. So we got something that's 39.0 meters here. We've got something that's 97.0 kilometers per hour. What's the 39 meters? Displacement. What's the 97 kilometers per hour? Yes, initial velocity. It actually says initial speed there, but we're not going to lose any sleep over that. If it's 97 kilometers per hour speed, well then it's 97 kilometers per hour in the positive direction velocity. So let's write down velocity just in case we need that. Anything else that we have here? Connor? Good. So this is stopping distance, so VF is going to be 0 meters per second. We're looking for the acceleration again. Let's convert the kilometers per hour to meters per second. Okay, we're getting really good at this now. 97,000 meters divided by 3,600 seconds. That gives me what? 26.994. 9444. All right, which one do you want to try, Lorraine? Same one, right? If it doesn't have time in it, we're usually going to use this. Yeah, that's a good question. Somebody said, who asked that? Isn't it speed? Yes, this equation does involve speed. And we wrote down our initial velocity and said we're looking for, wrote down our initial and final velocity. But if it's going in the same direction, then the initial velocity is going to be the same value as the initial speed, except that the speed's not going to have a direction. So it's easy to take a velocity and convert it to a speed here. We just wrote down velocity kind of just in case we need it. All right, let's look for A again. VF squared. VF is 0 again, so let's cross that off. 0 minus VI squared. Take the 2 times delta D over by dividing. So it becomes negative 26.944. Let's square that. Divide that by 2 times the displacement of 39.0 meters. Now let's see what we get. Let's say negative 26.9444 squared. Again, don't square the negative. Plus equals. Let's divide that by everything inside the brackets, 2 times 39 meters. And we end up getting negative 9.3 meters per second squared. Slowing down, so a negative number. Final answer should be, I've got negative 9.3. It should actually be negative 9.31. Anybody tell me why it should be negative 9.31? Michael? Yeah. Yeah, if we look back to our givens, 3 digits, final answer should be 3. If one of them was 2 digits, then the final answer should be 2. How would that change, by the way, if I said one of them was 2 digits and one of them was 5 digits? It should round to 2 digits, the least precise, right? Doesn't matter how good or how precise the best one is. What matters is how precise the worst one is. Right? Lorraine, is that kind of clearing things up a little bit for those? Anybody else for something else? 13 looking for displacement. Let's check here. Yeah, you're actually looking for distance, but if you find displacement, since the direction is not changing, it's going to be the same thing. And you're going to use the same equation there, I think. Yeah. VF squared is equal to VI squared plus 2AD. You're just going to solve for D instead of A. But the rearranging of that even is going to be real similar to what we've just done solving for A. All right. We started looking at this yesterday. Who remembers from yesterday what the shape of this graph represents? It's constant velocity, right? If that was a position time graph and it looked like that, what would it represent? Object at rest, object stopped. Okay, it's not a position time graph, so it means something completely different. Object at rest or constant velocity. Hey, if I wanted to create a position time graph that represented the same thing as this, what would that graph look like? Yeah, diagonal line there, right? Straight line, but on a slope. So these two graphs mean exactly the same thing. The reason they look different is because one's velocity, one's position. Take a look at the next one. Velocity time graph. What does this one represent? Yeah, acceleration, increasing velocity. If I was to plot a position time graph that represented the same thing, what would it look like? Caden? Okay. Curved upwards, good. Velocity time graph. This time we've got a straight line, but it's sloped downwards. What does this one mean? It's a negative acceleration, good. Position time graph. What's it going to look like? Somebody draw it out with the finger here. Good. Saw a couple people doing this. It's going to look something like that. Sometimes it's hard to see this, right? We're looking at two different graphs that mean exactly the same thing, but they look completely different. They mean the same thing, but they look entirely different. Next one, velocity time graph. What does this one mean? It's an increasing rate of acceleration. It's acceleration, but it's not just a constant acceleration. The rate of acceleration is increasing. A position time graph, it's hard to draw this one. It would also curve upwards. It would just curve upwards quicker. Does that make sense? And we have our velocity time graph that curves like this. Is the object speeding up here? Yes. So what does this mean? It's a decreasing acceleration. So it's speeding up, but as time goes by, it's not speeding up as quickly as it was before, but it's still speeding up. All right. I want you to take a look at what you see up here on the board right now. Okay. We're going to do another example, so don't even worry about copying this one out right now. Okay? I'm going to give you a handout in just a moment with an example on it, but then we'll go through that one. And it basically asks you for the same thing. Not quite as many questions, but more or less the same thing here. This is a velocity time graph as opposed to a position time graph. I've asked you for just about all of this stuff on position time graphs before. In fact, we had a quiz on it. Okay. Now we're going to ask you these same things with a velocity time graph. Let's see how we go about doing this. We want to find the velocity at a certain moment in time here. An instantaneous velocity, we call it. Yeah, I could have said for number one, find the instantaneous velocity at 1 second. How are we going to do that? Sorry? No. Connor? Up and over. On a position time graph, we could find the slope, or we could use v is equal to delta d over delta t, right? Both ways worked. This is not a position time graph. This is a velocity time graph. If we want to find the velocity at a certain moment in time, all we have to do is the same thing as we did for position on a position time graph. Now think about that. We wanted to find position on a position time graph at a certain amount of time. We went up and we went over. That gave us position. If we want to find velocity at a certain moment in time on a velocity time graph, let's go up and over and find velocity. Okay, that's about 1 second. Go up and over. We've got a velocity of somewhere around, looks like about 3.5. About 3.5 meters per second. Does that make sense? Does it make sense why we're not finding the slope? Because we don't need to, right? We don't need to. The value for velocity is already on the y-axis. We just have to find out which one we want. The position at 14 seconds, that should say the velocity at 14 seconds. What's the velocity at 14 seconds? How are we going to do that? Up and over. So this is 14 seconds, up and over. The position is going to be 4.0 meters. The velocity is 4.0 meters per second. What's the change in velocity now between 4 seconds and 8 seconds? How do we do that? Vf minus Vi. So up and over, do the subtraction. At 4 seconds, we've got a velocity of 8. At 8 seconds, we've got a velocity of 8. So the change in velocity there would be, somebody said it, 0 meters per second. Change in velocity between 0 and 2 seconds. Well, this is 2 seconds. This is 0 seconds. The final would be 8. The initial would be 0, so the change would be 8 meters per second. So far, so good? So we're doing pretty much the same things as we were doing on that position time graph, but we're doing it in different ways. Change in velocity between 10 and 12. Okay, this is 10. The velocity is 8 meters per second. The velocity here is 4 meters per second. The change in velocity is going to be what? What is it? Good, 4 minus 8. The final minus the initial, which is 4 minus 8, or negative 4 meters per second. It's a negative. It should be a negative. It's sloped downward, right? It's decreasing velocity. So it's a negative change in velocity. All right, what's the acceleration between 4 and 8 seconds? Suggestion on this one. The acceleration between 4 and 8 seconds, right here. Yeah, we can take the slope. There's another way to look at it as well. But the slope works. Good. That's the other way to look at it. Acceleration is equal to delta v over delta t. What's the change in velocity on that one? We already figured that out, right? 0. The time is 4 seconds, so the acceleration will be 0 meters per second squared. That should make sense. How do we know the acceleration is 0 without even doing a calculation? If it's constant velocity, it's got to be an acceleration of 0. Why don't we use 8 seconds? Because we're finding the acceleration between 4 and 8. So the change in time there, the time interval, is only 4 seconds. 8 minus 4 is 4 seconds. Okay? The acceleration between 0 and 2. Okay, we can use the slope for this, or we can use delta v over delta t. The change in velocity between 0 and 2 is 8 meters per second. We already found that up here. The change in time is 2 seconds, so that's going to be 4.0 meters per second squared. The acceleration between 10 and 12. A is equal to delta v over delta t. Between 10 and 12, we have a change in velocity of negative 4 and a time of 2, so that's going to be negative 2.0 meters per second squared. Tell me why it's a negative. I mean, mathematically, we just found that it's negative, right? But tell me conceptually why it should be a negative value. Right? Right. The velocity is decreasing. That means it's decelerating, therefore a negative acceleration. Good. The displacement between 0 and 16. This is a tough one. This is something that's completely different than anything you've done before. Any ideas? You may have done this in Science 10, I'm not sure. Any ideas as to how to find this displacement between 0 and 16 seconds? Good. Did you learn that in Science 10? Okay, good. Good. Now the area beneath this, it's kind of tough in this one because there's a lot of different shapes there. I don't know an equation, a single equation that is, that'll find me the area of this entire graph. So we've got to break this up into sections. Let's break this up into a triangle. We'll call that section 1. This a rectangle. We'll call it section 2. This triangle is section 3. And then this rectangle right here is section 4. The area of the first triangle, A1, is 1/2 base times height because it's a triangle. So that's going to be 1/2 of 2 times the height of 8, which is going to give me 8. And the units would be meters. Oddly enough, we're finding an area, but it's not meters squared because it's displacement. So the units are meters, 8 meters. How far did we travel in the first section there? 8 meters. What about the second section? What's the equation for the second section? Sorry? Base times height, or length times width, because it's the area of a rectangle. The base goes from 2 to 10, so the base is 8. The height is also 8. We multiply those together, we get 64 meters. The area of the third triangle is 1/2 base times height because it's a triangle. The base goes from 10 to 12, so it's going to be 2. And the height goes from 4 to 8, right, from 4 up to 8. So that's going to be a height of 4. Multiply those together, we get 4 meters. And finally, section 4, we've got to find the area of that. It's a rectangle, base times height. The base goes from 10 to 16. That's going to be 6. And the height goes from 0 up to 4. Multiply those together, we get 24 meters. Now what? Now we do what? Right. Add them together. 8 plus 64 plus 4 plus 24, 28, 36. It's 100, isn't it? I think it's 100. Does that make sense? Let me tell you right now a very, very common mistake that's made on position time graphs. Why am I going back to that right now? Because the mistake is made because of what we just did, right, Michael? A position time graph, we found displacement before, and it's easy. All we do to find displacement on a position time graph is say final position minus initial position. Up and over, subtract them. But what a lot of people will do starting now, when you get a position time graph to find displacement, is try to find the area. That's wrong. That's correct for a velocity time graph, but it's wrong for a position time graph. Does that make sense? None of this stuff is incredibly difficult, but once we start seeing both graphs, position time and velocity time, people start getting confused a little bit. That's why I'm suggesting to you that you don't memorize how we do something here. We don't memorize that we do A is equal to delta V over delta T to find the acceleration or whatever. We think about it. We understand it. And then we're more likely to get it correct if we see both graphs together. All right, question 10, the last one. The average velocity between 0 and 16 seconds. Any suggestion on that one? Average velocity. No, Vf minus Vi would be the change in velocity, right? What do we always do to find average velocity? What have we always done to this point, and what will we always continue to do to find average velocity? Nope. Not Vf plus Vi divided by 2. Displacement over time. V is equal to delta D over delta T. The average velocity is the displacement over the time. Is this easy? Yeah, it should be, because we have the displacement. We just found it. The displacement is the area. The time is 16 seconds. So 100 divided by 16 is, I don't know, 6.25. Sometimes the velocity is positive. Sometimes it's 0. Sometimes it's negative. Sorry, it's always positive, but sometimes it's increasing. Sometimes it's decreasing. Sometimes it remains constant. Bottom line is the average works out to be 6.25 meters per second. That make sense? All right. If you copied that down, that's great. If you haven't, that's fine too. We're going to do another example right now. That I did not want to provide the solutions for quite yet. So we'll cover those up. This one appears on a worksheet that I'm going to hand out to you right now. Okay? So we'll go through this together. That'll be your example, and then I'll have you work on a few more of these velocity time graphs by yourself. Right? Let me hand those out now for you. All right, we're taking a look at the question on the front side of this worksheet right now. This is our example that I want to go through together, and I want you to copy up the answers for. It's a velocity time graph, not a position time graph. Remember that. We find a lot of the same things, but the way we find it is entirely different for some of these things. What is the velocity at t is equal to 4 seconds? How do we do that? Up and over. So let's go up and over at 4 seconds. Up and over. The velocity at 4 seconds looks to be about 15 meters per second. What's the change in velocity over the entire graph? Well, the change in velocity is Vf minus Vi. The final velocity in this graph looks to be about 33 meters per second. The initial velocity is what? Looks to be about 3, I think. About 3 meters per second. It's hard to tell in this graph. It's not a great graph because it doesn't have enough grid lines. But it's about 3, I think. If this was a quiz and you said 4, then I'd probably mark that right because it's kind of hard to tell, right? So when we do this, the change in velocity ends up being equal to 30 meters per second. What's the acceleration over the entire graph? How do you find acceleration? We can say delta v over delta t, good. Or we could also say the slope, since it's just one straight line. Let's go with delta v over delta t, though. Delta v is 30 meters per second. The time interval is 10 seconds. So that's going to be 3.0 meters per second squared. And we want to find the displacement. How do we find displacement? If it was position time graph, how would we find displacement? Okay? Final minus initial position, right? Up and over, subtract the 2. It's a little bit more complicated on this one. We've got to find the area. So let's find A1. It's a triangle. 1/2 base times height. The base here is 10. The height goes from 3 up to 33, so the height is going to be 30. That's going to give me 150 meters. The area of the second section is a rectangle, so it's just base times height. The base is 10. The height is 3. So we add those up, it's going to give me 30 meters. What do we do with them now? Add them up, we get 180 meters. Sir, go ahead. What's your question? Very good. What else could I have asked you here, but I didn't? Really, the last thing that I could have asked you is the average velocity. The average velocity would be the displacement, which is 180 meters, divided by the time, which is 10 seconds. So the average velocity here would be 18 meters per second. The question is, where do we get the second area here? The second area is this little rectangle down here that we see. Let's erase some stuff there. Okay, that's a rectangle, and then we've got a triangle up here. We can't find the area of all that together because it's just an odd shape. We don't have an equation to describe the area of that shape. So we have to break it into two nice, easy sections, triangle and a rectangle. Does that make sense? All right, finish copying that out, and then I'll flip the page. Or sorry, no, I won't flip the page because you've got a worksheet in front of you. So finish copying that out, and then take a look at the other side of that sheet and do questions 1 to 4 on that worksheet, please.